On March 23, 1989, the Journal of Electroanalytical Chemistry published the article entitled Electrochemically Induced Nuclear Fusion of Deuterium. The authors are Martin Fleischmann, Professor of Electrochemistry at the University of Southampton, and Stanley Pons, Professor of Electrochemistry at the University of Salt Lake City. The history of cold fusion begins from that date. The authors state that they obtain a quantity of thermal energy much greater than that introduced with the electrolysis of heavy water, and that this excess cannot be justified by any chemical process. Their idea starts from three fundamental elements. First, the cathode is palladium. 2. Electrochemical reduction of deuterium involves the absorption of a deuterium atom into the palladium lattice. Third, the deuterium atom in palladium behaves like a charged species. The Fleischmann and Pons experiment foundations. The left image is the original device presented by Fleischmann and Pons. It is a calorimeter that also functions as an electrolysis cell. The temperature of the electrolyte at a given input power compared to the calibration curve at the same power determines the extent of any excess. It is a power balance. The output power must consider not only the thermal power generated by the electrolysis, but also the contributions of the heat removed toward the outside. From the gases generated by electrolysis, from the steam of heavy water, and from the heat transmitted by radiation to the outside. These contributions can all be evaluated with great accuracy. The Fleischmann experiment access heat measurements. By way of example, the calibration curve of a calorimeter similar to the one shown previously is given, which show the unique dependence of the temperature on the power input from the internal heater. In that calorimeter, electrolysis is now running with the generated thermal power P input, and the observed temperature is higher than that expected from the calibration curve. This implies that a process is taking place in the calorimeter to which the calibration curve corresponds to a higher input power. The excess power then is given, as shown, by the difference of the two values. The Fleischmann-Pons experiment. White palladium cathodes. The palladium-hydrogen system is well known for forming solid solution with hydrogen and its isotopes. It's shown that at room temperature and atmospheric pressure, 8.85 cubic centimeter of palladium, corresponding to 106.4 grams, absorb a volume of hydrogen in the atomic state which is 994 times greater. The system of hydrogen absorption isotherms as a function of the ratio of hydrogen atoms to palladium atoms shows three phase regions. Alpha phase at values close to zero of the hydrogen-palladium ratio. Biphasic system consists of alpha plus beta over a wide range of the palladium-hydrogen ratio. As the hydrogen pressure increases and the temperature decreases, one exits the biphasic domain where only the beta phase exists. The adsorption of hydrogen into palladium is due to migration into the interstitial sites of the cubic phase-centered lattice of palladium. Two types of sites are occupied as a function of the hydrogen-palladium ratio. Octahedron size 1 per cell, constituting the alpha phase, and the thetaedral side 8 per cell, which make up the beta phase. The Fleischmann and Pons experiment. Why the palladium cathode? The first two cathodic reactions compete in the formation of adsorbed deuterium. The absorption process is favored by the increase in the surface activity of deuterium and by the diffusion rate of deuterium in the palladium lattice. The accumulation of deuterium on the surface favors the desorption of deuterium as a deuterium gas. The level of confinement of deuterium in palladium depends on several factors that are not easily controllable. In general, they are influenced by the chemical purity of electrolyte solution and the impurities present in the palladium that should be less than 10 parts per billion. Further, the reduced palladium structural imperfections, cleaning of surfaces and their catalytic activation to increase the specific surface area, conduction of electrolysis by choosing the optimal current density is just an empirical way. The Fleischmann and Pons experiment. Why the palladium cathode? It was known since 1929 as the Kuhn effect that palladium, in the presence of hydrogen, does not behave as a pure electronic conductor, as expected for a metal, but presents mixed conduction because it's a conductor for hydrogen ions. The consideration reported in the article by Fleischmann and Pons is highlighted here, in which the proton state of hydrogen inside palladium and its mobility given by the high value of the diffusion coefficient are underlined. This state is unique in cases of a metal-hydrogen interaction. For comparison, the diffusion coefficients of the proton at 25 degrees C in liquid water and that of the hydrogen atom in iron in the solid state are reported. The difference in order of magnitude illustrates the peculiarity of the hydrogen-palladium system. The excess heat. The most significant evidence of the experiments performed over the years on the model of those of Fleischmann and Pons is that the excess power measured increases as a function of the deuterium-palladium ratio indicators of the various electrolysis cells tested. The data are substantially connected in a curve that grows almost exponentially. It should be noted that the graph shows thousands of experimental data obtained in different laboratories around the world, not always obtained following the same experimental methods as Fleischmann and Pons. Note that the curve has further enriched with consistent data over the years. Why still skepticism? The vexed question about cold fusion was and still is, given that no physical and chemical phenomena can and do not be responsible, what is the nature of excess thermal power? The presence of deuterium nuclei made one thing from the beginning of nuclear fusion reactions as occur in the vacuum between high-energy particles and in the stars at very high temperatures. In particular, the reactions considered were the following. Numerous experiments, such as Fleischmann and Pons, report the almost always non-reproducible presence of either tritium or neutrons or helium-4, but in no case does the number of particles detected justify the excess power measured in the same experiment. This aspect, as well as the difficulty of reproducing results, constitute the sore point of cold fusion. All this in the absence of any established theory. The theory that seems or seemed more convincing, but still not fully developed, unfortunately due to the premature death of the author in 2000, is that of the theoretical physicist Giuliano Preparata. The theory explains, on the basis of a quantum electrodynamics, which describes all the phenomena involving charged particles interacting by means of the electromagnetic field, the possibility that in condensed matter two deuterium nuclei can interact by overcoming the Coulomb barrier. Formation of a highly excited helium-4 nucleus, which releases its energy to the lattice mainly in the form of heat, in a time less than its lifetime, which is about 10 to the minus 21 seconds. According to the theory, this is possible in the presence of a coherent plasma made up of deuterium ions and electrons of the electronic structure of a palladium. The theory also explains the presence of a threshold in the value of the deuterium-palladium ratio and the existence of the gamma phase. The appearance of this phase would be justified by the decreasing trend of the relative electric resistance of palladium when the deuterium-palladium ratio tends to 1. The palladium-deuterium or palladium-hydrogen system does not behave like a pure electronic conductor, but as an ionic component, as we have already seen. The presence of these ionic components is responsible for the growing part of the graph. I am Daniele Gozzi, former full professor of physical chemistry of this department. Here I spent almost 50 years of my life, first as a student and until my retirement doing research and teaching. In the spring of 1989, as a spectator and actor, I experienced the beginning of a scientific adventure which immediately involved, with great intensity and for a few years, the international scientific community, and which still continues to interest a smaller number of researchers. It's my desire, I believe shared by colleagues and students of the time, to leave in the department at the Primo Levi Museum a testimony as representative as possible of the research and experimentation activity carried out by the group starting in 1989 and continuing for a few years. More than 30 years after 1989, a definitive word on cold fusion has unfortunately not yet been written. The work of many researchers and the research institutions has not produced that initially too exalted dream of obtaining energy in a relatively easy, affordable, and cheap way. It was not a collective delusion on a planetary scale, as some have claimed. There are many criticisms that can and must be attributed to the people, to the events of that historical period, but it would be intellectually dishonest to deliberately ignore a result for which there is not yet a scientifically acceptable explanation. I am referring to the phenomenon of excess heat. It's a result widely reproduced over time, obtained with different experimental methods by researchers scattered in laboratories all over the world. Take, for example, slide number 8 in movie number 1. What then is the prevailing criticism? The absence of the energy balance. In fact, the energies of any process of a chemical, physical, or chemico-physical nature conceivable in the system under examination are much lower than the excess heat measured. To justify the energy involved, possible nuclear processes have been invoked and extensively studied. If one follows this path, one finds that the sum of the energies associated with the various nuclear products normally found in modest quantities is also in this case less than the excess heat. The excess heat is therefore always greater. The natural question therefore follows: what is the hypothetical fuel and where are the ashes of this combustion? From this mainly derives the skepticism that surrounds the matter, and there is a tendency to liquidate everything with the generic argument whether it is a question of experimental artifacts or fraudulent behavior. Reproducibility, understood as a science requires and imposes, unfortunately does not exist, but as the history of science has repeatedly demonstrated over time, reproducibility manifests itself when the nature of the phenomenon has been understood. For practical reasons, it's not possible to represent all the work done by my group, which is however available in the literature, in publications in international journals, and presentation at national and international congresses. Here, I limited myself to showing our latest results, which were obtained with the most complete and the complex experimentation, which we had progressively expanded and improved over the years. The most relevant result, but it's not the only one that emerges, above all because by its nature it's free from any conceivable artifact, is that an X-ray film was impressed and in a very singular way during the electrolysis with a palladium cathode of a water alkaline solution. Under the same conditions, with a platinum cathode, the same film was not exposed. It should be emphasized that this occurred while the system was producing excess heat only in the cell with the palladium cathode. To impress a film of that type requires a radiation with energy about 3 orders of magnitude higher than the energy necessary to sustain the electrolysis of water, even if it was heavy water. I end this dutiful introduction by thanking and quoting in the following pages all those who took part in that adventure, those who collaborated in various capacities, and the institution that financed it. Thank you. March 23, 1989, Martin Fleischmann and Stanley Pons announced their results of excess heat in electrolysis with a palladium cathode in an electrolyte consisting of a lithium tetroxide in heavy water. Great media clamor follows for the announced nuclear-related phenomena. Experience in my electrochemistry group led us to repeat the experiment, but there was no nuclear capability. I involved the group of nuclear physicists from the National Institute of Health and the local branch of the National Institute of Nuclear Physics. At the end of April, it was possible to prepare a very artisanal experiment with a didactic neutron detector and an electrolysis cell in which it was not possible to measure the excess heat but only the temperature of the electrolyte with a K-type thermocouple. The cathode was sintered palladium. This was a substantial difference with that of a Fleischmann and Pons. That acquisition was with chart recorder. During one night, a consistent increase in temperature and a burst of the neutron counter were recorded. The following morning, the cell was without electrolyte because it was completely vaporized. The mere consumption of heavy water at set electrolysis current did not justify what happened. Despite all the precautions not to attribute any importance to the event, because I was personally skeptical and suspicious of some experimental artifacts, the news spreads. From that moment, an adventure lasting more than 7 years will start. Professor Giovanni De Maria, director of the Center of Chemical Thermodynamics at High Temperatures of the National Research Council at the Chemistry Department, encouraged me to continue by supporting the initial expenses, allowing me to participate in important international events. I then obtained a small grant from the European Community and subsequently a grant from the President of the National Research Council for the chemical part, and for the nuclear part, the National Institute of Nuclear Physics financed my colleagues from the National Institute of Health. This allowed me to set up a dedicated laboratory on the ground floor of the Canizzaro building of the Chemistry Department, visible in the video number 9. All the results obtained in those years are published and presented at international and national conferences. The research group and the publications. How the research group was constituted in the first period. For the chemical group, we have Giovanni Balducci, Riccardo Caputo, Fabio Cellucci, Pierluigi Cignini, Guido Gigli, myself, and Massimo Tomellini. For the nuclear physics group, Evaristo Cisbani, Salvatore Frullani, Franco Garibaldi, Francesco Ghio, Massimo Iodice, Giovanni Maria Urcioli. And these are the publications produced in that period. The will to continue the experimentation with the same level of complexity achieved and the fondest wish to maintain the quality of the results obtained up to then soon became unsustainable, together with the simultaneous lack of funding and the necessary human resources. To this was added the impossibility of the group of nuclear physicists to continue the collaboration because they were engaged abroad in high-energy physics experiments. This situation forced us to make a choice: continue the cold fusion experiments under condition of low control and the poor quality, or concentrate the experimental and the residual human resources still available on the palladium hydrogen system, which is key point of the Fleischmann and Pons experiments. The choice which seemed more reasonable to us was the latter. The first stage was that of the realization of a thermostated apparatus suitable for the measurement of the absorption and desorption of hydrogen from small-sized palladium samples for the construction of the hydrogen content curve towards hydrogen pressure. The calibration and characterization of this equipment is described in the degree thesis in chemistry by Francesco Di Pascasio, who passed away in 2021. The next stage was characterized by more complex experiments for the study of hydrogen loading in palladium under the action of a cold hydrogen plasmas produced in corona discharge regime, even with reversed polarity between the palladium electrode and the counter electrode. In this experiment, the effect of tensile loads on the sample with and without plasma and the presence of an internal electric field in the palladium sample was studied. These measurements were important for understanding the mechanical and the chemical physical effects on palladium sample under the action of outer and inner electric fields in hydrogen. These activities were developed by new recruits who over time took turns to obtain the degree in chemistry: Claudio Chiappini, Cristiano Trionfetti, Barbara Panella, and Andrea Baldi, with the collaboration of Francesco Di Pascasio. Acknowledgements: Chemistry Department of the University of Roma La Sapienza, which supported the logistical aspects of the experimentation and which now, with its museum, will preserve some fragments of that activity. Professor Giuliano Preparata, who died in 2000, a theoretical physicist who was a great enthusiast of cold fusion with his theory, perhaps laid the foundations for understanding the phenomenon. Professor Martin Fleischmann, deceased in 2012, I recall with pleasure the very interesting scientific discussion with a man of a remarkable scientific culture. Professor Giovanni De Maria supported me in the activity with enthusiasm, encouraging me in the most difficult moments, also supporting me in the search for funding. Collaborations, in particular with the Study Center of High Temperature and Chemical Thermodynamics of the National Research Council in the Department of Chemistry, the National Reference Laboratory for Heavy Metal Synthesis of the Istituto Superiore di Sanità in Rome, Centro Sviluppo Materiali of Castel Romano in Rome, Electrical Power Research Institute in Palo Alto, California, for gamma prompt measurements and neutron activation analysis. Funding: Directorate General for Research of the European Commission, Chemistry Committee of the National Research Council, section of the Nuclear Physics Institute at the Physics Laboratory of the Istituto Superiore di Sanità. This denomination that no longer exists, or with names that have changed over the years. Our latest results. This is the first transparency of my speech as the first invited speaker at the 6th International Conference on Cold Diffusion held in Sapporo in October 1996. I stressed the need to focus the research on shedding light on the discrepancy between excess heat and the energy associated with the nuclear products. In other words, the energy balance. I announced that shortly thereafter I would show the attempt that we made in the direction of the energy balance through three important quantitatively evaluated experimental evidences. What were the three important experimental findings? The first is the measurement of excess power by flow calorimetry. The second, the measurement of helium-4 by high-resolution mass spectrometry. The third is the impression of a film for X-ray with evaluation of the energy involved after calibration with a standard camera for X-rays. An important aspect is the time correlation of the three phenomena. It was a complex experiment which lasted 952 hours with 4 cells identical in structure, 3 of which with a palladium cathode, but each with a different geometry, and the other as white cell with platinum cathode. At 552 hours from the beginning, the blank cell number 1 and cell number 4 were wrapped with X-ray film. The results of our latest experiment were reported in the article entitled X-ray heat excess and helium-4 in deuterium palladium system. It was published in the Journal of Electroanalytical Chemistry. The first page of the article is reproduced here. The adventure of the previously cited article, which was published in the Journal of Electroanalytical Chemistry in 1997, the article appeared with incorrect layout of the figures and many typographical errors, despite the fact that all of these had been corrected by me in the proofs. I asked Elsevier to produce new proofs to check if the correction has been made correctly. The answer was that it was not necessary. The article was published with many typographical errors and some other incorrect layout. I protested vigorously with Elsevier, who republished the article the following year in the correct form, apologizing for what had happened. Despite all this, even the republished article still contains some typos. The determination of nuclear products. The nuclear reactions between the deuterium nuclei in vacuum are the following. The determination of tritium and the neutrons did not pose particular difficulties. Tritium was determined with a liquid scintillator in heavy water produced by the catalyzed recombination of deuterium and oxygen in the gaseous phase, leaving each cell. no possibility of environmental contamination. Neutron was determined with a high-efficiency neutron counter built at the Jomar Corporation of Los Alamos, on project by the nuclear physicists colleagues. The reliability of the counts was based on the discrimination between a neutron of a cosmic nature and from any environmental electrical interactions. The determination of helium-4 unfortunately posed more difficulties and required more attention due to the quantitative ratio helium-4 deuterium is expected very small. The concentration of helium-4 in air is 5.24 part per million. Possible environmental contamination. Mass spectrometric determination of helium-4 in presence of deuterium. The spectrum in the figure represents the separation of helium and deuterium in a one-to-one mixture. The axis of mass is purely arbitrary, and this point of the separation between the two peaks is located in the valley at 4.0111. Since the mass difference between helium-4 and deuterium is only 0.0256 units, in the presence of large quantities of deuterium compared to helium-4, the separation of the respective peaks would be impossible. It's necessary to remove most of the deuterium by means of a getter and an activated carbon trap at the temperature of liquid nitrogen. With this procedure, the measurement of traces of helium-4 becomes possible and sufficiently accurate. Neon as a marker of helium-4 from air contamination. The experimental system was designed and built to safely determine the possible production of helium-4 associated with excess heat. The basic requirement was to avoid any air contamination in the gaseous mixture generated by the electrolysis. The helium-4 content in air is 5.24 ppm. In case of detection of helium-4, especially if at a concentration comparable to those of helium-4 in air, it was necessary to identify the source. The concentration of neon in air is 18 ppm. Presence of neon together with helium-4 implies contamination. Higher resolution mass spectrometry identifies a mass of neon 20 in an area of a spectrum where other species appear clustered around this mass, which make their determination difficult. It was then decided to follow the spectrum around mass 10. It has neon 20 2+, where there is no significant interference. The high-resolution mass spectrometry measurements were performed in multiple ion detection mode, so ionic currents versus time. They were helium-4, the valley between helium-4 and deuterium, and deuterium and neon 2+. The control of the ion current corresponding to mass 4.0111 is a key parameter to ascertain the real separation between the peaks of helium and deuterium. The last experiment, the overall scheme. To simplify the diagram, the circuit for a single cell is shown. The experiment was with 4 cells connected in parallel for the supplies of nitrogen, heavy water, and the thermostated water. The series connection only for electrolysis current. Each cell had its own analog data acquisition and the digital channels for the event management. The gaseous mixture leaving each cell was connected to the respective catalytic recombiner, The function of a catalytic recombiner is to make offline determination of tritium in recombined EV water and the measurement of electrolysis efficiency by the volume of EV water recombined and amount of electrolysis charge at the time t. The flow of the cell being measured was automatically directed to the deuterium abatement system unique for all the cells. Graphical representation of the results of excess power and helium-4 measurements. For each cell, two graphs are shown, one upper and one lower, both with the same time scale. The upper one reports on the left ordinate the electric power fed into the cell for the electrolysis, and on the right ordinate we find the excess power obtained through the calibration curve of that cell and evaluated as mentioned in video number 1. The lower graph shows the measurement of helium-4 expressed in units of teraatoms, that is 10 to 12 helium atoms. There are 4 electrolysis cells and all with anode made of cylindrical platinum mesh, while the cathode is of platinum only in cell number 1 of white. In the others, the cathode consists of bundles of palladium wires in number and the diameter as shown in the table. Let's go back to the reference white cell in the upper right graph. The excess power is in the noise and similarly in the lower graph for the helium-4 measurement. The data acquisition started 200 hours before the activation of the electrolysis in the 4 cells. I remember that they are connected in series and they work in galvanostatic conditions, that is, by varying the current and not the potential difference between the anode and cathode. It's indicated for cell number 1 and also for cell number 4 the exposure interval of both to the X-ray film. The difference between the cells with the palladium cathode compared to the white cell can easily be observed also qualitatively. Heat excess versus helium-4 and apparent no-time correlation. The previous graphs, such as the one for cell 4 reproduced here, show that significant values of helium-4 often do not coincide with excess heat. It must be considered that the measurement of excess heat is almost continuous measurement. The acquisition interval is 60 seconds. The measurement of helium-4 is discontinuous. A large volume of the gaseous mixture coming from the electrolysis is not analyzed. In the experiment of about 950 hours, 382 samplings were carried out, each of 150 cubic centimeter of mixture consisting of nitrogen, deuterium, and oxygen corresponded to 5.73 10 to minus 2 cubic meters under normal conditions, to be compared with 2.24 cubic meters under normal conditions of a mixture flowed throughout the experiment. Thus, only about 2.6% of the mixture was analyzed. Helium-4 and the energy balance, time profile simulation of helium-4 from the cell to the quadruple mass spectrometer. In order to find a time correlation between the recorded excess power and the experimentally unsynchronized helium measurements, some tests were carried out to determine the helium transfer profile from a given cell to the mass spectrometer, maintaining the same operating conditions of the real experiment. The procedure consisted of injection at interval of time into one of the cells of a 10 cubic centimeter of air at the atmospheric pressure and at 20 degrees C. The input is equivalent to 1.27 10 to 15 helium atoms. The atomic fraction of helium in air is 5.24 parts per million. The helium content is measured by the quadruple mass spectrometer. The time profile accumulated by the N injection is well represented by this function. This implies that if helium were generated in equal and time-spaced events, the maximum value would be revealed at the time given by this relationship, where T0 is equal 0 in the graph. Helium-4 and the energy balance, instantaneous generations of helium-4 and their transfer to the quadruple mass spectrometer. Having previously acquired the helium transfer profile from the cell to the mass spectrometer, we can think of a correlation model between these two quantities, excess power and helium. Thus, it's assumed that the excess power is generated at a certain times Tpi, and at the times Tsi, sampling of the gaseous mixture takes place. The time required for sampling is given by this equation, which is essentially depends on the volume of the sampling cylinder, which is 150 cubic centimeter, and on the flow of the carrier, which is a nitrogen, which transfers the gaseous mixture, leaving the cell to the mass spectrometer. The nitrogen flow is constant. Delta T is therefore the minimum time window where the helium measurement is performed. The helium atoms present in the sampling volume are the sum of all the contributions of the helium formation events that occurred in the time delta T from the beginning of the sampling. The total number of helium atoms, NSI, is given by this relation. The figure schematically shows this type of reasoning. In the equation below, the summation is extended to the number of points where the excess power was measured. Since the time required for sampling is much greater than the time difference between the excess power measurements, it can be shown that the number of helium atoms is given by this equation. This QR number is the power associated with a nuclear reaction event between deuterium nuclei to generate helium-4. Helium-4 and the energy balance comparison with excess power. Through the previous correlation, it can be seen that the transition from the upper graph, which represented the experimental trend of the excess power and the measurement of helium, to the lower graph, where the time correlation between the helium and excess power is reported. As a result of the elaboration that we have done to the model, it can be seen that there is a rather significant correspondence between the excess power and the helium. The ratio of a measured helium to calculated helium is shown in this graph. It's clearly seen in the insert in the graph that basically the energy balance is satisfied within the experimental uncertainty, since this ratio is between 0 and 1. The processing of the helium measurements is congruent with the excess power, and the ratio between the measured and the calculated helium is compatible with the uncertainty associated with the calculation of the diffusion of helium in the transfer from the cell to the mass spectrometer. Evidence of electromagnetic radiation emission. This is a strong evidence of an chemical phenomenon. This is the X-ray film that was placed in contact with the cell 4 after 552 hours from the beginning of the experiment. The duration of exposition was 7 days. The film was then analyzed by microdensitometry after calibration with a standard X-ray camera. The three-dimensional representation of this film show practically what appears on the film on the ZX plane, while the exposure value is shown on the Y-axis. In other words, this is the blackening intensity of individual spots. Now, there are a number of questions that need to be answered. Why an exposed region between spots? Why spots? This will be treated after in the slide A, B, C. What is the energy of the radiation? How much total energy was released? What is the nature of the radiation? And finally, it should be remembered that the same type of film that wrapped the white cell was not exposed. Why spots? To explain the presence of spots in the film, the position of all systems components relative to X-ray film must be considered. The figure shows the simplified plan diagram of the arrangement of the cells, and in particular not only the position of cell 4 with respect to the film, but also and above all the arrangement of the internal components of the cells. The cells were contained in a perspex torus in which thermostated water circulated. The torus was itself inside the neutron detector. In the same figure, there is a table listing all the materials with their respective thicknesses and densities, starting from the palladium cathode up to the inner wall of the outermost circumference of the torus. The usefulness of the data in the table will soon be understood. The scale drawing shows the position of the cell with respect to the film and in the center of the torus. It's important to observe the position of the cathode, which you remember is a bundle of palladium wires. At the center of the cell, with respect to the 1 mm diameter platinum rod, represented in plan view by the green circle, which supports the cylindrical platinum network which forms the anode. For simplicity, neither the cathode nor the anode are shown in the figure. If the cathode emitted the radiation totally absorbed by the platinum, but completely transparent to the other surrounding materials, this would produce a shadow cone such as to obscure all the emissions generated in that solid corner. The distance between the two nearly parallel sets of spots measured on the film is 7 mm plus or minus 0.05 mm. Why an exposed region M between spots? As we have already seen, the measurement of an exposed area between the spots made directly on the film is 7 mm. The calculation can be made from the geometry of the system, and the value of 7.67 mm is obtained. So a ratio between the two values that differs by about 9.6%. This difference is due to the shape of the cathode, the respective positioning of the electrode, which modifies the value of the distance f between the anode and the cathode. Furthermore, following the electrolysis, a deformation of the electrode is created. Shown here is the cathode of the cell 4 after 952 hours experiment compared to the electrode before the experiment. The X-ray film was analyzed with a microdensitometer with steps of 600 microns on the z-axis and 50 microns on the x-axis. The measurement of the optical density of the spots in Röntgen exposure units took place by calibration with known exposures of the same type of film and developed with the same procedure. White spots, Section A. The shape of this and distribution of the spot is not compatible with palladium X-ray diffraction. To obtain this, a source having an energy of 21.61 kiloelectronvolts is needed, and in the system under examination, the maximum energy involved is the potential difference between the electrodes, which is the order of 3 to 5 electronvolts. Are the material interposed between the palladium cathode and the X-ray film capable of fully absorbing this radiation? This can be verified by making a fairly simple calculation, as long as you know the interposed materials, their thickness and their density. The thickness corresponds to the optical path of the radiation. It's necessary to know the dependence of the photon energy of the respective mass absorption coefficients. The intensity of the transmitted radiation I, with respect to the incident 1 I0, is given by this relation written in red, where ρ I is the density of an ith material. The figure shows that at the K threshold energy of palladium, only the interposed material, even without palladium, would completely absorb the radiation. In fact, we see that at 21.61 kiloelectronvolts on the YPD curve, at that energy, the transmitted intensity is 0. Therefore, it means that the interposed materials would totally absorb that radiation. As an example, if we put ourselves at 150 kiloelectronvolts, the presence of a thickness of 875 microns of palladium would attenuate the radiation by 50%. White spots, Section B. Findings and hypotheses more compatible with the spot structure. Outside the shadow cone, the radiation source cannot be on the surface of the electrode because this would produce a diffuse and a no-spot blackening. let us consider the multi-wire structure of the cathode, in particular of a cell 4 made of 150 wires of 250 microns in diameter. This structure can be represented as in the figure and is presented as a pseudo-HCP structure with 7 shells. The optical path of the radiation, whose source is inside, may or may not be formed by slits. In path A or path B, the two optical paths are distinguished by situations of reduced or total attenuation of the radiation. The total case is that of path B. The most realistic hypothesis is the presence of multiple point sources on the surface and/or inside some wires, but not in the outer ones. The system is therefore a set of virtual slits which are illuminated by the radiation according to its angle of propagation. The existence of such slits is in the domain of the shortest palladium optical paths. The existence, positioning, and intensity of the spots depends on the domain of the slits, on the positioning of the sources, and on the optical path, as well as on the energy of the radiation. The figure shows the attenuation value of radiation of 90 kV if the source were at the origin of a coordinated, expressed in microns at 0.0 or at 433 and 750 of the HCP structure in another shell, that is, the fourth shell. In the latter case, the attenuation is lower because the optical path is shorter. The optical path associated with each spot is obtained from the microdensitometry measurement of the film, known the geometry structure of the system. Here, the calculation is represented by this equation written in red, where L phi I is the x-coordinate of the IT age spot measured from the central axis between the two spot distribution. White spots, section C. The figure compares the real distribution of the spots with the distribution calculated through the simulation. As we see, there is enough correlation between the real and the calculated situation. The relation to the position of the film with respect to the cathode and the previous equation, it's possible to estimate the position of the sources which generated the spots on the film. This is represented by the red dots in the figure. It should be noted that none of these are found in the outermost wires, and the major densification is in an intermediate region of the HCP structure. It is evident that the distribution of the sources is expected to be uniform. The representation shown here was obtained in relation to the positioning of the X-ray film with respect to the cell. Calculation of the minimum energy of the radiation. The total attenuation is given by this relationship in red. The total radiation attenuation can be separated into the contribution A and B. A is the component of the attenuation independent of the position of the sources and is the same for all spots. B is the attenuation inside the palladium cathode, which depends on the radiation path in the palladium itself. It should be remembered that the palladium cathode consists of a certain number of wires. Realistically, each spot originates from the same elementary event. Therefore, I0 is the same and the intensity depends only on the path of the radiation in the palladium. More intense spots are those generated by more external sources, but not the surface of the cathode, and therefore the ratio I max on I0 can be determined. The least intense spots are generated in the most internal position, and therefore the ratio I minimum on I0 can be determined. The dependency of energy of the palladium mass absorption coefficient is given by the exponential relationship written in blue. Combining the ratios of I maximum and I minimum using the previous equation B, the energy value can be obtained which, as we can see, depends on the difference between the shortest and the longest paths and on the ratio of the maximum and the minimum intensities. Obviously, T minimum and the T maximum must be included in the alpha angle which generates the shade of M, the one shown in the previous diagram, which corresponds to the maximum distance between the spots at a constant Z. The simulation shows that the greatest accumulation of sources is located where the red points are. As we have seen previously, for symmetry reasons, in order to calculate the minimum energy value, we set minimum Phi equal to 250 microns. This means that the source is on the surface of a wire in the sixth shell. There is in the outermost shell, but not in the last. The maximum is set equal to 1875 minus 250, that is 1625 microns, which is the source at the center of the HCP system. Under these conditions, the minimum calculated energy of the radiation is 89 kiloelectronvolts. Higher Phi minimum values, but within the constraint imposed by the system, would give a value of about 135 kiloelectronvolts. What event generated the radiation? A first hypothesis, the energies of the K-alpha lines as a function of the atomic number indicated that the estimated energy value is closer to the K-alpha lines of lead and bismuth. Since the value is underestimated, the K-alpha levels of the first elements of the actinide series could also be considered. Numerous analytical investigations carried out with ion-coupled plasma mass spectrometry, with a detection limit of the order of nanograms per liter, have not shown any trace of these elements, and therefore to exclude that the radiation is generated by electronic transition typical of X-ray radiation, but by nuclear processes. The nuclear process that was initially considered, as described in our article in the Journal of Electroanalytical Chemistry, was based on the need to make the presence of alpha particles, helium-4, the estimated energy value of 89 kiloelectronvolts, and the presence of palladium coexist with its stable isotopes in natural abundance, including palladium-105 at the level of 22% about. The reaction of an alpha nucleus with palladium-105 to give cadmium-109, which is an unstable nucleus, which through electronic capture is transformed with an half-life of 453 days into the unstable isotope silver-109. Its transition to stable isotope of silver takes place with the emission of a gamma photon of about 88 keV and with an half-life of about 40 seconds. The scheme is apparently satisfactory because it agrees with the estimated energy value, but seems to be impossible due to the low cross-section of the alpha particle process. The most recent hypothesis. This is the first page of the article entitled "The Case for deuterons stripping with the metal nuclei as the source of the Fleischmann-Pons excess heat effect." The article is by Dr. Thomas Passel, published in the Journal of Condensed Matter Nuclear Science. In this article, our work on the evaluation of radiation energy was explicitly mentioned. In 2014, Dr. Thomas Passel, an expert nuclear physicist at the Electrical Power Research Institute in Palo Alto, who had examined our results very carefully, wrote me a letter in which he proposed a different interpretation of the generation of radiation. The scheme coincides in the final part, but differs in the initial part proposed by us. The starting stable isotope of palladium is not palladium-105, but palladium-108, which by reaction with deuterons produces the unstable isotope palladium-109, which converts into metastable silver-109, as indicated here in the diagram. Palladium-108 is an isotope with 26% in natural abundance. The scheme then coincides with the transition to stable silver with emission of the gamma photon of 89 keV as the energy estimated by us. The proposed scheme is supported by a well-established nuclear physics of the reaction called the proton-deuteron stripping. The following article is a guarantee from a scientific point of view. The most recent hypothesis, but in any case they are from 1935. Here is the first page of the article published on Physical Review and entitled Note and Transmutation Function for Deuterons. The authors are Oppenheimer and Phillips of the University of California, Berkeley. The scheme experimentally demonstrated by the two authors is that in which an atom with atomic number colliding with a deuterium nucleus produces an atom with the same atomic number but with an increase in mass of 1 unit, releasing a proton. That is why they are called proton-deuteron stripping reactions. It's an example of the possibility of transmuting one atom into another while maintaining the same atomic number, thus forming an isotope of that atom. This was Dr. Pastel's proposed mechanism for our reaction, and with that scheme, the energy value we found is justified. Here are some details of the flow calorimeter cell system. In particular, we see the two temperature sensors. The one on the left measures the inlet temperature of the water at a constant temperature. The sensor on the right measures the temperature of the outlet water after passing through the interspace between glass tubes B and C, inside which there is a coil which increases the exchange surface. A vacuum is present between the glass tubes A and B to ensure thermal insulation of the whole system. The last experiment, the overall scheme. To simplify the diagram, the circuit for a single cell is shown. The experiment was with 4 cells connected in parallel for the supplies of nitrogen, heavy water, and the thermostated water. The series connection only for electrolysis current. Each cell had its own analog data acquisition and the digital channels for the event management. The gaseous mixture leaving each cell was connected to the respective catalytic recombiner. The function of a catalytic recombiner is to make offline determination of tritium in the recombined heavy water and the measurement of electrolysis efficiency by the volume of heavy water recombined and amount of electrolysis charge at the time t. The flow of the cell being measured was automatically directed to the deuterium abatement system unique for all the cells. Comments on the following video. The place. It's room 55 on the ground floor of the building Cannizzaro, which is the oldest building of the Department of Chemistry of the University of Rome, La Sapienza. The spaces. Room 55 is large and is divided into 3 rooms of different sizes. For convenience, we indicate Room A was the larger one, but which was not fully used for the experiment. Room B, on the ground floor, is about 1/3 the size of A and has a ceiling height of about half that of A, in any case greater than 2 meters. Here all the hardware part of the experiment had been developed. Room C is above B. Here the entire control and acquisition part of the experiment was developed. It has a slightly smaller surface area than B, and the height of its ceiling added to that of B is approximately equal to the ceiling of A. C is reached by stairway starting inside A. The registration. It was made on April 2, 1995, Sunday, by myself. Total assembly had been completed a few days ago, and a series of control tests had begun. The quality of the video is not excellent, but there is more than one explanation. If I remember correctly, at that time digital cameras weren't available yet, and in any case, I had a cassette tape camera which I bought in New York in 1993. In the video you can see, Room C, that the monitors of the 3 computers in operation are inserted in a metal box made of mu metal, material which shields the magnetic field. The monitors of that time were cathode ray tubes, As is known, the trajectory of electron is influenced by the magnetic field. An nuclear magnetic resonance spectrometer equipped with a powerful superconducting magnet in liquid helium was in operation in the adjacent laboratory. The lines of force of that field partly entered our laboratory. That Sunday, I realized that my camera was also affected by the field, and therefore I was forced to shoot looking for the position of the minimum interaction. The noises. There are mainly of two species. Room B is dominated by the combined continuous noise of the rotary pumps and the turbomolecular pump of the mass spectrometer, as well as periodic noises of a various actuator. In room C, predominantly the acoustic of cosmic neutron counting and the instrumental beeps. Bearing in mind the description of the laboratory previously made, here we are in room A, and the first shot concerns the rack cabinet where all the control electronics of the neutron detector are contained. An interface then starts from here which connects the data acquisition to the upper floor. The more detailed description of the neutron detector is reported in an article whose references are cited at the end of video 8. Instead, room B can be glimpsed, where a large white cylinder is visible. It's the neutron detector inside which is all the experimentation. Here it is. There is a tangle of wires covering the vision of 4 cells. This white space where you see this circumference inside which are contained 6 stainless steel tubes containing helium-3. They are neutron counters with a central electrode at 1000 volts with respect to the stainless steel tube. These 4 stainless steel cylinders, each of which contains a catalytic recombiner of the deuterium-oxygen mixture, here the recombinant EV water is collected and then subsequently analyzed for the presence of tritium. Then follows the gas line coming from each cell. Here the entire gas sampling apparatus is visible, which consists of an automatic system controlled by one of the computers to divert the gas flow of the cell under examination to the sampling. The visible stainless steel cylinders have a volume of 150 cubic centimeters. The collected volume is diverted to a stainless steel container filled with size getters alloys and subsequently to another stainless steel container with activated carbon and in liquid nitrogen, as visible in the blue dewar. The function of these 2 stages is to drastically reduce the deuterium content to make possible the determination by mass spectrometry of helium-4, especially if in trace amounts. As seen previously, the mass spectrometric separation of deuterium by helium is critical. The introduction of gas into the mass spectrometer is regulated by a low vacuum system such as to create the optimal working conditions in the spectrometer chamber. Upon command, the opening of the inlet needle valve into the spectrometer. The spectrometer chamber always works around a pressure of 10 to minus 9 millibar. The pressure gauge inside the chamber controls the closure of a needle valve if the pressure rises above a preset value. It can be observed that all the connections are made with swage-locked pipes to ensure. In addition, we are now upstairs in room C. Here you see some power supplier. It is the rack cabinet on the left there. Are various instruments that it would take too long to describe individually. The most important one is the data logger, which is this one. It can capture up to 60 analog channels and a further 30 digital input channels. There are other ancillary instruments such as this one, for example, which is a counter of the charge that passes through the cells during electrolysis. I remember that the electrolysis takes place in galvanostatic conditions and the current is varied during the long experiment. This is to verify the efficiency of the electrolysis in relation to the consumption of EV water. Some of the instruments present are of our own design and homemade. Below there is a rotary stills recorder that records the temperature of the four-cylinder heating system of the recombiner you have seen before. The first computer you see is a Macintosh FX running on a program made with LabVIEW. The assigned function is to acquire the shape of the pulse associated with each neutron detected by the neutron counter through the connection with the digital oscilloscope that you see. This is another Macintosh FX that also runs with a LabVIEW program for acquiring all the parameters of the cells in the experiment and controlling a number of functions. All this takes place through the connection via interface with the data logger. The data logger controls the maintenance of the electrolyte level in each cell through the laser beam level sensor. Another important control is the rotation speed of the pump, which ensures the constant flow of thermostated water in each cell. The accuracy of flow calorimetry depends greatly on this. These beeps you hear periodically are nothing more than the signal that the neutron count has detected. The display you see on the wall shows the neutron counts of the 12 groups of a counter, each consisting of 5 tubes of helium-3 at 6 bar. They are in fact 60. Inside the toroid, where the cells are arranged, there is a camera in the central part that rotates and can go and check the immersed part of the cells. This is the third computer. It's not a Macintosh that is directly connected to the mass spectrometer with a spectrum acquisition system. As has been described, the acquisition of the signal takes place with the multiple ion detection mode, that is multiple ion detection, in which we are able to detect the intensities of the selected ion species as a function of time. I remind you that the choice that has been made is to select, in addition to the deuterium, the valley between deuterium and helium and the neon 2+, because these are parameters that make it possible to check that the presence of helium does not derive from contamination from air. And here you see that the sampling has taken place right now. You can see that the pressure has suddenly risen because practically gas has entered the mass spectrometer. The small flow of gas that enters changes the pressure inside the spectrometer. After that, as the gas is pumped, the signal decreases. The signals that are required are represented as you can see. Some are signals that are the masses. The last three refer to the pressures, both within the spectrometer chamber and within the low pressure deuterium abatement system. Provisional conclusions on May 2023. It was an exciting experience that unfortunately did not produce definitive results. However, they demonstrate serious experimental evidences that cannot be sufficiently archived as experimental artifacts. Years later, the situation has not substantially changed despite the numerous international experimental confirmations of both excess heat and the nuclear phenomena. Reproducibility is still an issue. None of the proposed theories satisfactorily explains the nature and the diversity of the observed phenomena. Are low-energy nuclear reactions real? Are they acceptable according to current knowledge? New roads seem to be on the horizon. Like so many other stories of scientific research, to which time has since given answers, even the understanding of nuclear phenomena in condensed matter does not seem to be mature yet. Is cold fusion alive yet? Here is the whole list of international conferences on cold fusion starting from 1990 up to the present day. In fact, the next one will be in August 2023 in Poland. Judging from this list, it would seem that cold fusion has had a continuity over the years, and there is still many researchers who continue to work on it. All this suggests that this field is still alive. A new way for nuclear fusion in condensed matter appears in 2020 following the publication in Physical Review C of the article Nuclear Fusion Reactions in Deuterated Metals. The article describes the experimental results and the phenomenological explanation of the research conducted at the NASA Glenn Research Center. The abstract of the article is reproduced here. I highlighted the main aspect of the research idea, that is, the possibility of activating fusion in condensed matter in those systems where the concentration of deuterons is extremely high and which have an electronic environment due to the metal, particularly favorable to their shielding. The search for energy-producing devices for interplanetary missions led to the discovery of the lattice confinement fusion at NASA Glenn Research Center in Cleveland. Lattice confinement fusion is a room-temperature nuclear fusion process that does not require large investment and technological complexity. What does it consist of? The concentration of a nuclear fuel nuclei in a magnetic confinement fusion and in inertial confinement fusion is about 10 to 14, while in lattice confinement fusion is about 10 to 23. This is practically the Avogadro number. Why? Metals like titanium and erbium, like palladium, are absorbers of hydrogen and its isotopes. In particular, erbium absorbs deuterium up to erbium D3. The system is initially irradiated with 2.9 megaelectronvolt gamma photons, which produce the dissociation of deuteron into protons and neutrons. The energy transfer is from the neutrons to the static deuterium nuclei in the lattice, which are brought to an excited level D star. The electronic structure of erbium produces extensive shielding of a partially charged deuterium nuclei due to transfer of binding electrons to the F-band of erbium. This reduces the repulsion and promotes the fusion reaction rate. The process can take three different paths. In the BC process is a true nuclear fusion process, as helium-3 and a neutron are formed with an energy of 2.45 megaelectronvolts. The other two processes are transmutation processes. In fact, in the DE process, we have the transformation of erbium into thulium. This is called the screened Oppenheimer-Phillips stripping reaction because it is favored by electron shielding, or the real stripping reaction by Oppenheimer-Phillips, which is not a real transmutation, but is simply the passage from one isotope to the another with the production of a proton. This is a recently discovered process but contains points of contact with the cold fusion 34 years ago. They are metal saturated with deuterium from gaseous phase of deuterium. The system is a solid solution of deuterium metal. In cold fusion, this occurs by electrolysis in heavy water. The bond of palladium, titanium, erbium, and other metals with the deuterium and the hydrogen produces a transfer of electrons toward the metal, giving the system the property of a mixed conductor, electronic and ionic. In palladium, this has been evident since 1929 with the Kane effect. The numerous experimental data of nuclear phenomena and excess heat in cold fusion are found as the deuterium-metal ratio increases. The phenomena encountered in lattice confinement fusion with the erbium-deuterium-3 are in agreement with the elevated concentration of deuterium. Ultimately, cold fusion is nothing but a lattice confinement fusion. In 1989 and the following years, big science bitterly contested cold fusion. It's now good that NASA, Advanced Research Projects Agency Energy, and BEHIND have programs on low-energy nuclear reactions.